Today I'll be proving that the polynomial p of x equals the product of x minus a1, x minus a2, and dot 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 up to x minus an and subtracted by 1 is irreducible over the integers if all the numbers a1, a2 up to an are distinct integers. Okay. So to prove a polynomial is irreducible over the integers, we need to show that p of x, we can't write p of x as the product of two polynomials f of x and g of x, where f of x and g of x have integer coefficients and both of them have degree at least 1. Okay, so we want to prove we can't find polynomials f and g that satisfy these conditions. Okay, and to do this we can use proof by contradiction, where we can assume polynomials f and g do exist that satisfy the conditions, and we'll try to obtain a contradiction using this. So we can see, since p of x has degree n, so degree of p is equal to n, and since the degrees of f and g are at least 1, it means the degrees of f and g must be between 1 and n minus 1. And this is because f and g can't have degree n, or neither f nor g can have degree n, because the other one would have degree 0. Okay. What we can also see, if we substitute any of the ai's into p, we will have ai minus a1, ai minus a2 up to ai minus an minus 1, and we'll eventually have ai minus ai coming up, so this product will become 0, and we'll have 0 minus 1, which equals minus 1. This means for all values of I, we have p of ai is equal to, we can also write it as f of ai and g of ai. This equals minus 1. And now, since f and g have integer coefficients, and since ai is an integer, it means f of ai and g of ai are both integers. So we have two integers that multiply to give minus 1, and there's only two ways this can happen, and this is when f of ai, g of ai can either equal 1, minus 1, or minus 1, 1. We can also see in both of these cases we'll always have f of ai plus g of ai equals minus 1 and 1 add up to 0. So in both cases we'll always have f of ai plus g of ai equals 0 for all I. Okay, and now I will construct a polynomial hx, which is equal to f of x plus g of x. And this is to use the fact that f of ai plus g of ai equals 0 for all I. And remember, the degrees of f and g are at most n minus 1, which means degree of h, the sum of f and g, the degree of h must also be at most n minus 1. And now for all values of I, the h of ai is equal to f of ai plus g of ai, which is equal to 0, which means since there are the numbers a1, a2 up to an are all distinct integers, it means we have at least n distinct roots of h. So since we have at least n distinct roots of h, however, the degree of h is at most n minus 1. The only way this can happen is if h is a zero polynomial. So since the degree of h is less than the number of roots of h, the only way this can happen is if h is a zero polynomial. So you can just write sort of congruent symbol to denote it's a zero polynomial. And this means f of x plus g of x is the zero polynomial. So we have f of x is the minus of g of x. And from earlier we assumed p of x was equal to f of x g of x. And it follows, if we replace f of x with minus g of x, we have minus g of x squared. So it means minus g of x squared is equal to the x minus a1, x minus a2, dot dot dot, x minus an minus 1. Now we can compare leading coefficients on both sides. What we can see is, to find a leading coefficient of g of x squared, so just ignoring the negative sign at the moment, the leading coefficient of g of x squared, that's the same as the square of the leading coefficient of g of x. And you just square the leading coefficient of g of x. Okay, so this means this number is going to be positive. However, we have a minus sign over here, which means the leading coefficient of negative g of x squared is going to be negative. So the whole thing has a negative leading coefficient. And however, the right hand side has a leading coefficient of 1. This is because when you multiply all the x's, you will only have a leading coefficient of 1. And since 1 is positive, we have a contradiction. This gives us our final contradiction. And using this, it follows that f of x and g of x that satisfy the conditions that you can't find such f and g, so it means that p of x is irreducible over the integers. Okay, that concludes the solution to this polynomial irreducibility problem. So hope you enjoyed the video. Thanks for watching, and I'll see you next time.